Today's video covers section 12.4, which is the cross product. The cross product is going to remind you a lot of the dot product. This is a one-day section, so we're only going to spend one day covering it, and then we'll have a discussion day. Today's video is going to, first of all, review determinants of a matrix. Then we're going to talk about what is the cross product and how do we calculate it. We'll look at some properties, and then we'll also look at some applications of the cross product. So first thing that I want to review with you is determinants of a matrix. So let's consider the 2 by 2 matrix 1, 3, 4, 5. Now, if I want you to take the determinant, the way that I denote that, besides using the word determinant, is I'll put vertical bars. So if you see something like that, those brackets denote a matrix, but the vertical bars denote a determinant. So here's how you calculate a 2 by 2 determinant. You're going to calculate the product of the first diagonal. So we're going to have 1 times 5. Then you're going to subtract the product of the other diagonal. So 3 times 4. So we end up with 5 subtract 12, so we get a determinant of negative 7. So that's when we're looking at a 2 by 2 matrix. 3 by 3 matrix gets more complicated. So let's consider the 3 by 3 matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, I want you to calculate the determinant, so I'll put vertical bars. Okay, here's how this one works. You are going to start by choosing one row or column. In this case, I'm going to choose the first row. Next, you will look at the first element, and then you are going to ignore the row and the column that that element falls in. And you'll be left with the 2 by 2 matrix, that 5, 6, 8, 9. So we're going to take that 1, and we're going to multiply by the determinant of 5, 6, 8, 9. Then you're going to look at the second element, that 2. Again, you're going to ignore the row and the column that 2 falls into, and you look at the corresponding matrix, or the one that's left. So that's that 4, 6, 7, 9. So you'll be calculating the determinant of that matrix. Last element in the row is 3. Again, ignore the row and the column that 3 falls in, and you're left with matrix 4, 5, 7, 8. Now, a few other things for you to know. You're always going to keep the sign of the first element, opposite sign of the second element, keep the sign of the third element. So you're going to flip. And then you're ready to calculate. So we have 1 multiplied by this determinant, so 45 minus 48. Subtract 2 times this determinant, so 36 minus 42, plus 3 times the last determinant, so this is 32 minus 35. This ends up being negative 3. This is negative 6 times negative 2, so positive 12, and then negative 9. So we end up with a determinant of 0. This is going to work for any matrix that's 2 or bigger. So this is the same way that you would approach a 4 by 4 matrix, a 5 by 5 matrix, etc. We're only going to be looking at 2 by 2 and 3 by 3, but that's just to keep in mind for the future. Now, a few things to remember with determinants. First thing I want you to remember is that you only calculate the determinant of a square matrix. So 2 by 2, 3 by 3, 4 by 4. It's not possible to calculate the determinant of a 2 by 3 matrix, for example. And then there's 2 other points that I want you to remember that are going to help you with your calculations. First thing I want you to remember, if any 2 rows are the same, the determinant is going to be 0. So if you're looking for the determinant of a matrix where 2 of the rows are the same, you don't even have to calculate it. You know right away that the determinant is going to be 0. Other thing I want you to remember is if you interchange 2 rows in a determinant, that multiplies the value of the determinant by negative 1. So sometimes rather than choosing the first row, you might choose to use the second row for your 3 constants. When you use the second row and you switch the first row, it's going to multiply the determinant by -1. So hopefully that was enough of a review of determinants for you. If it wasn't, please make sure you go back and consult your pre-calc notes or you look at your textbook to review a little more in depth calculating a determinant. So that was your review. This is going to lead us to the cross product. We're going to start out with a definition. Let's consider that we have 2 vectors in 3 space. One of them is going to be A, and let's call the components A1, A2, A3. And then let's say that we have vector B also in 3 space with components B1, B2, B3. Then the cross product of A and B is the following. So first we need to talk about notation. An X is going to denote the cross product. So this is saying I'm finding the cross product of A and B. Next thing to note is that the cross product is going to give you a vector. The following are the components. A2B3 minus A3B2, A3B1 minus A1B3, and then the third component will be A1B2 subtract A2B1. Okay, so that's how we're going to calculate the cross product. Now, this is very cumbersome and difficult to remember. That is not the only way to show a cross product. So in fact, that's not the way that I use. The other calculation that you can use is a determinant. So the other way to calculate A cross B is the determinant of a 3x3 matrix. The first row of that matrix is going to be IJK. Second row is going to be the components of A. Third row is going to be the components of B. So I don't care which one you remember. If I were you, I would remember this one because it doesn't involve memorizing some seemingly random formula. But that's how we're going to calculate the cross product. So we're going to do an example where we calculate one, and then we'll look at what the importance of the cross product is. So for example number 1, we're going to consider matrix U, which is 1, 2, -2, and we're going to consider matrix V, which is 3, 0, 1. We are going to find both U cross V and V cross U. So let's do U cross V first. I'm going to do it the determinant way. So again, please make sure you use vertical bars and not brackets. If you use brackets, that denotes that you have a matrix. We want to show that we're finding a determinant. So first row is going to be IJK. Second row is going to be the elements of U, so the 1, 2, -2, and then the elements of V, so 3, 0, 1. Okay, so if I look at I first, I'm going to ignore the row and the column that I come in and look at the corresponding matrix, or the one that's left. So that's the 2, -2, 0, 1. For our next element, we need to flip the sign. So ignore the row and the column that J come in and look at the matrix that's left, which is the 1, -2, 3, 1. And then for K, ignore the row and the column that K come in, and we have 1, 2, 3, 0 left. This is going to be 2 minus 0, so we get 2i. This is going to be 1 subtract -6, so we get a positive 7, but we have that negative then, so -7j. And we have 0 subtract 6, so -6k. So this vector is U cross V. Next, you're asked to calculate V cross U. Now, if this were the dot product, we would end up with the same result. Not sure, though, if that's going to be the case with the cross product. So again, the first row is that IJK. Then we're doing V. 3, 0, 1. And then the elements of u, which is 1, 2, negative 2. Calculating the same way, so I have I, ignoring the row and the column. The matrix that's left is 0, 1, 2, negative 2. Subtract j, and then I have 3, 1, 1, negative 2. And then k with 3, 0, 1, 2. This is going to be 0 subtract 2, so negative 2i. Negative 6 subtract 1 is negative 7. With that negative, gives us a positive 7j. And then 6 subtract 0 is positive 6k. Okay, so what we're going to notice, first of all, is that we did not end up with the same vector both times. We have the same components but opposite signs. Now, is that always going to happen? Well, let's look what we did. We have almost the same two determinants that we're calculating, but we switched two of the rows. Now, remember the 2 points I told you before. If you interchange any two rows, it multiplies the determinant by negative 1. So that should make sense here. When you switch u and v, you're interchanging two rows, so it's going to multiply the value of the determinant by negative 1. So that, yes, will always be the case. Now, the question is, why do we even calculate the cross product? What's the importance of it? Well, it actually has a really important purpose. A cross B is going to be orthogonal to both vector A and vector B. So in a lot of applications, you may be asked to find a vector that's orthogonal to both A and B, in which case you're going to calculate A cross B, or B cross A. If I just ask you for a vector that's orthogonal to A cross B is still orthogonal to A. Now, let's think about this though for a minute. Let's say we have some vector A and some vector B, like this. There are two vectors orthogonal to both of these. There's the one that's coming out the video towards you, and then there's the one that's coming out of the video kind of, but going away from you. One of them is A cross B, the other one is B cross A. So it's important that we know the orientation of A cross B. Is it coming out towards us, or is it going away from us? And the way to find that is the right-hand rule. Now, this should sound familiar. You covered the right-hand rule, I believe, in physics. If you didn't, we did talk about the right-hand rule the very first day of the course. So here's what the right-hand rule says. If the fingers of your right hand curl in the direction of rotation, so what I mean by that is the direction that's less than 180 degrees, from A to B, then your thumb is going to point in the direction of A cross B. So in this case, I'm going to put my hand on B, and my fingers curl from A to B. That means that A cross B comes out of the paper at us. So you want your fingers to curl from A to B. A to B. The other way, if we went like this, it'd be B to A. So curling A to B, oh, and it has to be your right hand, coming out at us. Okay, so now that we know how to calculate the cross product and its first major importance, what I want to do is I want to talk about some properties. Okay, property number 1, and this is one that you've already seen. A cross B is going to be the opposite of B cross A, opposite in sign. Next, if I have some constant c that I'm multiplying by vector a, and then I cross by b, that's the same as first crossing a and b, and then multiplying by c, or taking c and multiply by the second vector and crossing the two. Next thing to know, if I take a and I cross it with the sum of two vectors, that's the same as first taking both cross products and then adding them. Likewise, if I take a sum and then I cross it by another vector, that's the same as first crossing and then taking the sum. I got two more. If I cross b and c and then I dot it with vector a, that's the same as first crossing a and b and then dotting it with vector c. Okay, and then this one is going to be the least intuitive. If I cross a, or if I cross b and c rather, and I cross a then with that resultant vector, that's going to be the same as a dot c multiplied by b subtract a dot b times vector c. Okay, so those are just ones to remember. I have a few more fun facts for you. First one is if I take a cross b, and then I take the norm of that vector. That's going to be the same as the norm of a times the norm of b times the sine of theta. So the sine of the vector between them. Now, remember from last section that if I have a dot b, that's going to be the norm of a times the norm of b times cosine of theta. That leads us to our next fun fact. A and b are parallel if and only if a cross b equals 0. Now, that should make sense. If a and b are parallel, then the angle between them is 0 or pi. Sine of 0 and sine of pi are both 0. So if the cross product is 0, that tells you that the two vectors are parallel. And then our last fun fact, which is going to lead us into our first application, is that the length of a cross b is equal to the area of the parallelogram determined by vectors a and b. So that's going to lead us into our next example. This will lead us into our second example. Find a vector perpendicular to the plane that passes through the points P, which is 1, 4, 6, Q, which is -2, 5, -1, and R, which is 1, -1, 1. Okay, before we do any calculations, I want us to look at what we're looking at right now. So we have some plane and it has these points P, Q, and R. Let's say maybe P is here, Q is here, and R is here. We want a vector that is perpendicular to this plane, the plane that passes through all points, all 3 points. So what we can think of is we could draw in this vector here, and we could draw in this vector here. Now, once we have 2 vectors, we know how to find another vector perpendicular to these 2. So let's start by finding these 2 vectors. We're going to find vector PQ. So this is the vector starting at P, heading towards Q. That's going to be P subtract Q, or Q subtract P rather. So I have -2 minus 1, 5 minus 4, -1 minus 6. So this will give us -3, 1, -7. And then we're going to look at PR. So the vector starting at P going towards R. So that'll be R minus P. So 1 minus 1, -1 minus 4, 1 minus 6. So this will give us 0, -5, -5. Okay, so now that we have those 2 vectors, we're going to need a vector perpendicular to those 2, which would then be perpendicular to the plane. Now this is where this section comes in handy. The first thing we know is that PQ crossed with PR, so that's going to give us a vector, and PR crossed with PQ, that's also going to give us a vector, are perpendicular to both PQ and PR, and therefore also the plane. So then what we can do is we can find one of those 2 cross products. So I'm going to do PQ cross PR. If you did PR cross PQ, that would also be correct. So we have I, J, K, -3, 1, -7, 0, -5, -5. Okay, so I have I. Ignore that row, that column, and the matrix that's left is 1, -7, -5, -5. Once I go on to the next element, I have to switch the sign. Ignore the row, ignore the column. We get -3, -7, 0, -5. And then we have -3, 1, 0, -5. Okay, so simplifying that, this is going to give us I. We have -5 subtract 35 minus J, 15 minus 0, 15 minus 0 again. Okay, so we end up with -40I, subtract 15J, add 15K. So that is one such vector that is going to be perpendicular to the plane. Of course, that's not the only answer. We could also have given the answer of PR crossed with PQ, which we've already talked about is going to be all the opposing signs. So that would have been 40, 15, and -15. Now, what's also important to note is any scalar multiple will also be perpendicular. So any scalar multiple will also be perpendicular. So what I mean by that is I can take that answer that we already got and I can divide it by -5, let's say, and instead have an answer of 8I, add 3J, subtract 3K. So if you look at any of the examples in your book or the examples in the packet that you do, a lot of times I'm going to simplify as much as possible. The book will simplify as much as possible, so now you know why. If you don't simplify, that's fine. It's just important to know that scalar multiples are also perpendicular. Okay, next example. So example 3. We are going to find the area of the triangle. Determined by P1, which is the point 2, 2, 0, the point P2, which is -1, 0, 2, and the point P3, which is 0, 4, 3. Okay, before we jump into any calculations, like with example 2, I would like us to look at a picture. So let's say we have P1 here, P2 here, and P3 here. We're going to notice that these three form a triangle, and we want the area of that triangle. Now, it's probably a good idea to start by calculating some of these vectors. So we have this vector P1, P2, and this vector P1, P3. So let's start with that. If we have P1, P2, it's going to be P2 subtract P1. So this will be -1 minus 2, 0 minus 2, and 2 minus 0, which gives us the vector -3, -2, 2. We also have a vector P1, P3. If you trust me, I will tell you that ends up being -2, 2, 3. Now, the question is, how does that help us? So obviously that's all we're learning in this section is cross product, so we know we're going to have to take the cross product probably. Now, if you remember, if I take P1, P2, and I cross it with P1, P3, and then I take the norm, what that does is it gives us the area of the parallelogram that's formed. Okay, so visually what's going on is when I do P1, P2, and I cross it with P1, P3, I get the area of this parallelogram right here. And then if I divide it by 2, it's going to give me the triangle that I'm actually interested in. Okay, so that's what we're going to start with. We have P1, P2 crossed with P1, P3. We have our IJK, -3, -2, 2, -2, 2, 3. Okay, so if I look at my I end up with -6 subtract 4, which will be -10. If I look at my J, I get -9 subtract -4, which would give me -5. But you have to remember with the J, you're flipping the sign, so +5. With our K, we get -6 subtract 4, so -10. Okay, now we want the area of the triangle. Please do not divide by a scalar multiple here. We want the triangle to remain the size that it is. So don't divide by a scalar, just leave it. So now we're going to find the norm of that vector. It's going to be the square root of 100, add 25, add 100. So I'm squaring them all, summing them. This is the square root of 225, which is 15. Now remember though that is the area of the entire parallelogram. We're only interested in the triangle. So the area then of the triangle is going to be 15 over 2. Okay, so that is the first 2 applications of the cross product, finding a vector perpendicular to 2 other vectors, and then finding the area of a triangle or a parallelogram. There is one more application of the cross product, and it's called the scalar triple product. Okay, scalar triple product. What that means is you have 3 vectors. You're going to take B and you're going to cross it by C. So that's going to give you some vector. And then you're going to dot that with vector A. So anytime you're asked to find a scalar triple product, this is what you're asked for. Now, from those properties that we wrote down before, that's the same as A cross B dotted with C. Now, one thing that's important for us to remember is that this is going to be a number. It's going to be a number, it's not going to be a vector. Because remember, this is a vector, but then we have a vector dotted with another vector, which is going to give us a number. Okay, so then the way to calculate this, if we have that A dotted with B cross C, it's going to be a determinant. First row is going to be the components of A, Second row is going to be the components of B. Third row is going to be the components of C. And then we're calculating the determinant. Okay, now, what is the importance of the scalar triple product? The scalar triple product gives the volume of the parallelepiped that is determined by vectors A, B, and C. Now, it's actually the absolute value of the scalar triple product. Sometimes the scalar triple product is going to be negative. So when you take the absolute value, it gives the volume of the parallelepiped. Now, before we do an example, we need to know what a parallelepiped is. Parallelepiped is a three-dimensional rectangular prism. It's like a rectangular prism, except it's kind of smushed. It's on a slant. So it's going to be something like this. So picture a rectangular prism, but one that's slanted. That's what a parallelepiped is. And this would be A maybe, and this would be B, and this would be C. Or rather, this could be C as well. So you have your three vectors, and together they form a parallelepiped. If you need another visual, you are welcome to look in your book, because your book has some visuals as well. Okay, so our last example. We are going to use the scalar triple product to show that vector A, which is 1, 4, negative 7, vector B, which is 2, negative 1, 4, and vector C, which is 0, negative 9, 18, show that all three are coplanar. Okay, so it's already telling us that we have to calculate the scalar triple product. So let's do that, and then hopefully that'll help us show that the vectors are coplanar. So we are going to do A dotted with B cross C. As I showed you above, that's going to be the determinant of the 3 by 3 matrix that has all three vectors. So we have 1, 4, negative 7, 2, negative 1, 4, and 0, negative 9, 18. Now, of course, you can plug this in your calculator and get the determinant on your calculator. I don't want you to do that. On a test, I'm not going to permit you a calculator, so you should know how to do this by hand. So what you're going to do, as always, you choose your row. So I have 1 times the determinant of negative 1, 4, negative 9, 18. Subtract 4 times the determinant of 2, 4, 0, 18, minus 7 times the determinant of 2, negative 1, 0, negative 9. So then I'm going to have negative 18 subtract negative 36, minus 4 times 36 minus 0, subtract 7 times negative 18 minus 0. Now, if you trust me, I will tell you that that ends up being 0. Okay, so what did we find out? What we found out is that we have three vectors, and they form a parallelepiped with a volume of 0, meaning they don't form a parallelepiped. So we know that the volume of the parallelepiped, that means we have three vectors that do not form a three-dimensional figure. They do not form a three-dimensional parallelepiped. The only way that could happen is if they're coplanar. So what this tells us is that vectors A, B, and C are coplanar. Okay, that is it for section 12.4. There's more examples in your book. You can also go on WebAssign as you're working through your homework and look at some of the tutorial videos. If you have any questions, please look in your book or email me.